Okay, so this lecture is going to be about conjugation in Sn, the symmetric group on n letters. We have seen before what the symmetric group is, and that every permutation in the symmetric group has a particularly nice and unique decomposition into disjoint cycles. On the other hand, we have seen in a previous lecture the general definition of conjugation. This was one of the fundamental examples of a group action. Briefly, let me remind you, this is if we have an element of the group G and X, which here the group is acting on itself, so X is also an element of the group, the action is given by Gx G inverse. And the orbits for this action are what we call the conjugacy classes. Now we want to see this action concretely. In the case of the symmetric group, it has a particularly nice decomposition that is amenable to computation. So let's suppose we have two permutations, sigma and tau, in Sn. And to begin, let me assume that tau has a particularly simple form. It is a k-cycle given by a1 up to ak. Okay, so these ai are integers between 1 and n. All right, now what we want to compute sigma tau, sigma inverse. And I claim that this has a simple answer. It is again a k-cycle. Okay, and which k-cycle is it? It is the k-cycle obtained by applying sigma, the one by which we are conjugating, to these ai. So it's just given by sigma of a1 up to sigma of ak. And so this is again a k-cycle. Now, how do we go about checking that this is correct? Well, these permutations, they are functions. It's sufficient and necessary to check that they have the same values on all points. So let's plug in something. Now, when I plug in something, I can plug in something of the form sigma of ai. If I have a number that is not sigma of something, then on the right, this k-cycle fixes it, and then it's easy to see that also on the left it's fixed. So this is the interesting case to consider. And so then what is this? Well, you see, conveniently we have here the sigma and the sigma inverse. So these are going to cancel out. And so this is sigma tau of ai. But now, by the definition of the permutation given by a cycle, by the definition of what cycle notation is, tau of ai is just the next one that appears in the cycle. So this is simply sigma of ai plus 1, where we understand this to mean that if ai were equal to ak, then we would have, we put ai plus 1 to be a1. We put ai plus 1 equals ak plus 1 equals a1. That's what this parenthesis here is saying, that the next one is this one. Okay, so we have, we end up with sigma of ai plus 1, but now look at this new k-cycle with the sigmas. What is it saying? It is exactly the permutation that maps sigma AI to sigma AI plus 1. That is, sigma of A1 goes to sigma of A2 and so on. So now let's read what we have here. This sigma tau sigma inverse, it takes sigma of AI to sigma of AI plus 1. That's exactly what this K-cycle is doing, so the claim is correct. So I'll put a check here that the claim is correct. Okay? So what have we learned? We have learned that if we conjugate a K-cycle by any permutation, we get again a K-cycle, which is just obtained by applying that permutation inside the K-cycle. Now, more generally, if I replace tau assume tau is no longer just a K-cycle, but tau in Sn arbitrary, okay, then I can write tau as tau 1 up to tau m, the cycle decomposition. I can write this as a product of disjoint cycles. And now I use the general fact about conjugation in any group, that conjugation is an automorphism. So what do I mean by that? We had the general equation gx g inverse up there. Now if I do gxy g inverse, well, this is just gx g inverse times gy g inverse, because this term here reduces to the identity. And so you see that this is, what is this saying? This is saying that conjugating a product xy is the same thing as conjugating the first thing in that product and then conjugating the second thing. Of course, you have to conjugate by the same element. So this is in any group. Now we apply this in our situation. We have sigma tau sigma inverse. This is sigma, now tau is now our product, tau 1 up to tau m, sigma inverse. And by what I wrote here in any group, I can write this as sigma tau 1 sigma inverse up to sigma tau m sigma inverse. And now each of these tau i's, they are some ki cycle, and we can apply what we did there. So this conjugation, it's going to be a product of a cycle of the same length as tau 1 times a cycle of the same length as tau 2 up to a cycle of the same length as tau m. And concretely, we can compute each of these explicitly by that rule over there. Okay? So now let's immediately do an example. Okay, so let's take a permutation tau that is a product of more than one disjoint cycle, so that we see the full thing in action. So let me take maybe 1, 2 times 3, 4, 5. And just for fun, let me think of this as an element of the symmetric group on 6 letters, not on 5 letters, so 6 is being fixed. And now I need to choose a sigma. Let me maybe choose for sigma, the 4 cycle 1, 3, 4, 2. So this I will also think of it as an element of S6. And now I will compute sigma tau sigma inverse. So if we want to write this out concretely, this is 1, 3, 4, 2 times 1, 2, 3, 4, 5. And now I need to write down sigma inverse. Now, remember that it's very easy to compute the inverse of a case of any cycle. So I just go the other way. So I can put the 1, and then instead of going like this, I just go the other way. So I have 1, 2, 4, 3. This is sigma inverse. All right, and now one thing we can do, and I suggest for you to work this out, is we can actually do the multiplication. We'll start with this one, then do this one, then do this one, then do this one, composition of functions. And we'll get something, but we can also use what we learned above and just apply this sigma inside. And so I have that. Let me write this out carefully so that you see what's going on. So I have sigma of 1, sigma of 2, this 2 cycle times the 3 cycle, sigma of 3, sigma of 4, sigma of 5. Okay, and then just by seeing what sigma is, so sigma of 1 is 3, sigma of 2 is 1, sigma of 3 is 4, sigma of 4 is 2, sigma of 5. 5 does not appear in the notation for sigma. That means that 5 is fixed by sigma. So sigma of 5 is 5. Now, if we want to rewrite this, it's sometimes nice to rewrite your cycles so that the first number that appears on the left is the smallest one. This is not obligatory, but we could also rewrite this as 1, 3 times 2, 5, 4. Notice that here I have to be careful. I can't just do like 2, 4, 5. That would be a different 3 cycle. I have to maintain the cyclic order of them. That means 5 comes after 2. It should continue to come after 2, and so on. Okay? And in this example, it's still manageable to actually compute out the product. But you can see that now if instead of S6 we go to S20, then it will become a real pain to do the actual multiplication. But with this simple observation, doing the conjugation is actually quite simple. Okay, so now that we've seen an example, and I encourage you to work out many more on your own, let's, for example, recap the main theoretical thing that's going on here. So what we have seen is that let's call them something else, not to be confused with what we did before. If x and y in Sn are conjugate, then x and y have the same cycle type. So what I mean by this is that if, say, x is a product of 2 disjoint 3 cycles and a 5 cycle, then y immediately we know is of the same kind. And by using the same type of argument that I did, just sort of running it backwards, we can see also that conversely, it's not hard to see by the same argument the other direction, that if x and y have the same cycle type, then they are conjugate. And concretely, how would we do this? We would just set out to find our sigma conjugating x to y. But we would use what we did above. So we decompose them into cycles, and then we say, oh, we want a sigma that maps, you know, this to this according to what's going on inside the cycles. Okay, but so the conclusion is that two elements in Sn are conjugate if and only if they have the same cycle type. Another way to say that is that the conjugacy classes in Sn are precisely the sets of elements of some given cycle type. Okay, so now let's see an example of this conclusion. Okay, let's do, as an example, let's do the case of S4. So how many cycle types do we have in here? So cycle types. So if you think about it, to give a cycle type, it's the same as writing 4 as a sum of positive integers, where you can have repetitions, and you're allowed to have 0. So I can have, let me explain what I mean by writing it out in this example. I can have 4 is equal to just 4, okay? And so this corresponds to 4 cycles. I can have 4 equals 3 plus 1. Now, the 1 cycle is just elements that are fixed, so this corresponds to 3 cycles. I can have 4 equal to 2 plus 2. So this corresponds to a product of 2 disjoint 2 cycles. So we would also call this type 2,2. We have the identity, which is 4 equals 1 plus 1 plus 1 plus 1. So this is the identity. So this is the trivial cycle type, if you want. And now let's check, have we forgotten anything? So we can to check if we've forgotten anything. In arguments about the symmetric group, it's very easy to forget something. It's very easy to make some mistake in the combinatorics. Let's check if we've forgotten something. Well, a good way to do that is to add up the number of elements. The number of elements should always add up to the order of the group. The order of Sn is n factorial. The order of S4 is 4 factorial, which is 24. Let's think about the number of elements in each of these conjugacy classes. To give a 4 cycle, well, here's an example of one. To give such a thing, I have 4 choices for the first number, 3 for the second, 2 for the third, 1 for the fourth. But I have to be careful. I have to divide out by, remember that if I have 1, 2, 3, 4, this is equal, for example, to 2, 3, 4, 1, because I've only cyclically permuted what's going on. So there's 4 ways to do that. So I should divide here by 4, and what I get is 3 factorial, which is 6. So for 3 cycles, we similarly, so we have 4 for the 3 cycle is like 1, 2, 3. I have 4 choices for the first element, 3 for the second, 2 for the third. Now there are 3 ways to cyclically permute that do not change the permutation. So I have 4 times 3 times 2 divided by 3 is 8, 3 cycles. Moving on to 2 cycles. So here, an example of a 2 cycle would be 1, 2 times 3, 4. How many of these do we have? So I can do this. I can also say I have 4 for the first one, 3 for the second one, 2 for the third one, going from left to right, say, and 1 for the fourth one. But now I have to be careful with the number of divisions that I do. So I can divide by 2 for the fact that 1, 2 is equal to 2, 1. So I'll divide by 2 here. I can also divide by 2 for the fact that 3, 4 is equal to 4, 3. And finally, I can divide by 2 for the fact that 1, 2, 3, 4 is equal to 3, 4, 1, 2. Now, you have to be careful here. A common mistake at the beginning is that if we were doing type 2, 3, if we were doing type 2, 3 and S5, then I would not have an additional division here. I would have 5 factorial. I would divide by 2 for 1, 2 equals 2, 1. So my example would be this now. I would divide by 3 for this 3 cycle, but I would not divide by 2 because if you think about, you have to think a bit on your own about this, but if I'm counting things that look like this, not things that look like a 3 cycle times a 2 cycle, even though this is giving me the same permutation. So there I would just have this. So I would get 20. Now, going back to in S4, here we do have a third 2 coming from the fact that these 2 disjoint cycles are of the same type. They are both 2 cycles, while here we have a 2 cycle and a 3 cycle. Okay, so long story short, now we have this 8 canceling out with this 8. We have 3 of these. The identity, we have 1. How many do we have? 14 plus 4 is 18. That's smaller than 24. So we forgot something. What did we forget? We forgot we can also write 4 as 2 plus 1 plus 1. Here, it's good because we see it's not completely trivial like the 4 equals 1 plus 1 plus 1, but we have more than 2 terms, and we also have different numbers appearing, and you see this 1 is repeated. And so this corresponds to the 2 1s are saying that 2 are fixed, and the 2 is saying we have a 2 cycle. So these are just two cycles. And our example would be 1, 2. And then the number of 2 cycles we compute like the number of 4 and 3 cycles. The number of 2 cycles is 4 times 3 divided by 2, which is 6. And good for us, 18 plus 6 is equal to 24. Now we got the correct order of the group. This is a good way to suggest that we did this problem correctly, and we did. So here we have the possible cycle types for S4, which means we have computed all the conjugacy classes of S4 by the conclusion above, and we have even calculated the number of elements in each conjugacy class.